Welcome back, Design Junkies. School taught you to fear failure. The real world will reveal failure is your greatest teacher. This episode of Mechanical Engineering Made Simple comes to you by a listener request. If you didn't know, we do those. So if there's a topic you want us to break down, explain, or explore, just drop us a comment. We prioritize getting the content you want in front of you. So let's dive into today's requested topic. We are taking a massive stack of listener questions and condensing them into, well, a single brutal reality check.
Yeah, a reality check is definitely the right word for it.
Right, because right now, somewhere in the world, there is a flawlessly engineered, mathematically perfect 500-ton pressure vessel sitting on a barge. I mean, the CAD model was flawless. The finite element analysis was entirely green.
All the colors on the screen were exactly what the engineering manager wanted to see.
Exactly. But because of a single, 1-inch miscalculation in the diameter of a lifting pin, or just a fundamental misunderstanding of how a wave trough multiplies apparent gravity, that vessel is about to tear itself off the deck. It's going to sink the barge and bankrupt the project.
And the scary part is, it happens far more often than anyone in this industry wants to admit.
Wait, really?
Oh, absolutely. We spend thousands of hours analyzing the operational stresses of a fluid inside a machine, but we entirely gloss over the violently chaotic reality of how that machine is, fabricated, inspected, and transported.
Right, because it's easy to just look at the screen.
Yeah, a perfect CAD model is a wonderful thing on a screen. But if that design cannot survive the welding arc, or the radiographic inspector's interpretation, and the open ocean, it is nothing more than expensive digital abstract art. We are dealing with factual, truthful mechanics today. No pretty promises.
Okay, let's unpack this. Because the gap between digital perfection and physical reality, it really starts the moment you print the blueprint. I call this the blueprint illusion.
I like that, the blueprint illusion.
Yeah, because before any massive structure can be built, it has to be drafted. And the biggest pain point I see young engineers running into is assuming a mathematically perfect 3D model translates directly to a perfect physical part on the shop floor.
That is easily the most dangerous assumption you can make. The fundamental disconnect is that university mechanics courses, they treat materials as mathematically continuous, right, and geometrically perfect.
So they teach you that a 1-inch hole is exactly 1 inch.
Exactly. But the physical shop floor operates in a world of entropy. A 1-inch hole is actually a highly complex, totally irregular cylinder.
Oh, good, the drill bit chatters and stuff.
Right. Its diameter varies from top to bottom. It might lean slightly to the left. The location of its center shifts depending on the thermal expansion of the steel in a hot machine shop, or even just the microscopic wear on the drill bit over the course of an 8-hour shift.
Which is exactly why the American Society of Mechanical Engineers, or ASME, created the Y14.5 standard for geometric dimensioning and tolerancing GD&T.
Yes, and it's not just a suggestion of how to draw lines on a paper. It's a rigorous, legally binding language.
It defines exactly how much physical imperfection is legally allowed before you have to literally throw the part in the scrap bin.
And yet, it is a language that is routinely misunderstood by so many people. To even begin speaking GD&T, you have to establish a physical coordinate system in reality, not just on your computer screen.
Right, the datum reference frame.
Exactly, the datum reference frame. Whenever you have a physical part floating in space, whether it is a tiny aerospace bracket or a massive engine block, it possesses 6 degrees of freedom.
Okay, let's break those down for everyone. You have your 3 translational degrees, right? Movement along the X, Y, and Z axis.
Yep, so moving forward and backward, sliding left and right, and moving up and down.
But what always trips people up are the 3 rotational degrees of freedom. Pitch, yaw, and roll around those exact same X, Y, and Z axes, usually denoted as U, V, and W in kinematics.
Right, so consider what happens when a machinist or an inspector tries to measure a physical part. If you just set a block of machined steel on a flat granite surface plate, you haven't actually locked it down.
You've only constrained 3 of those 6 degrees of freedom.
Precisely, because the granite table, which acts as the primary datum plane, it stops the block from falling through the table along the z-axis, and it stops it from pitching and rolling.
But I can still take my hand and just slide the block around on the table in the X and Y directions.
Right.
And I can spin it like a top around the Z-axis.
Which means your measurement origin is still floating. It's useless. To fully constrain the part, you must push it against a secondary datum.
Like a perfectly perpendicular metal fence bolted to the table.
Exactly. That eliminates the ability to slide in the Y direction and stops the spinning. That's 2 more degrees of freedom gone. Finally, you slide the block along the fence until it hits a tertiary datum, like a physical stop at the end.
And that constrains the final x-axis translation.
Right. Only when all 6 degrees of freedom are locked in the datum reference frame can you actually establish true position.
But man, I've reviewed drawings where the engineer referenced datums in a way that makes physical measurement literally impossible.
Oh, I see it all the time.
They'll call out the center axis of a theoretical hole as the primary datum, but you can't physically rest a part on a theoretical axis on a granite table.
No, you cannot touch a theoretical axis. But let's dive into the concepts that cause the absolute most heated arguments between engineering and manufacturing. Maximum material condition, or MMC, and least material condition, LMC.
Oh boy, yeah, the material condition modifiers.
They're the most powerful tools in ASME Y14.5 and honestly the most frequently abused. Maximum material condition is the condition where a geometric feature contains the absolute maximum amount of material permitted by its specified tolerance limits.
So, to make this tangible, if I am designing a steel shaft that has to slide into a hole, the MMC of the shaft is when the machinist turns it to its largest allowable diameter.
Correct. It has the most physical metal left on it.
Conversely, the MMC of the hole it goes into is when the hole is drilled at its smallest allowable diameter.
Yep.
Because a smaller hole means less metal was actually removed from the block.
Yes. And that combination, the largest possible shaft attempting to mate with the smallest possible hole, is your absolute worst case scenario for assembly.
Because if it fits, then it'll fit always.
Exactly. If your design works at MMC, you guarantee that any other combination of shafts and holes within the tolerance band will also fit together seamlessly.
And then least material condition, or LMC, is simply the inverse.
Right. It is the state where the feature contains the least amount of material, so the smallest shaft and the largest hole.
I see LMC used a lot when structural integrity is the primary concern rather than assembly. Like, if you are drilling a hole near the edge of a pressure-containing wall.
You want to calculate the stress based on the largest possible hole, which leaves the thinnest possible wall.
That is the exact application for LMC.
Yeah.
But the true genius of Y14.5 is how these material conditions interact with positional tolerance.
Oh, the bonus tolerance concept, yes.
This brings up my absolute favorite way to visualize positional tolerance at MMC. Think about parking a car in a standard home garage.
Okay, I love this analogy.
If you were driving a massive, lifted, heavy-duty SUV, that vehicle represents maximum material condition. It has the most material. Because it's so large, your positional tolerance for parking it perfectly straight inside that garage is incredibly tight.
It's almost zero.
Yeah, it's almost zero. If you veer an inch to the left or right, you are ripping the side mirrors off on the garage door frame.
A perfect constraint mechanism.
But take that same garage. Instead of the SUV, you pull in on a tiny dirt bike. The dirt bike represents a significant departure from maximum material condition.
Because it has so much less material.
Right. And because the bike is so small, your positional tolerance for parking it grows massively. You can park that bike crooked, totally sideways, or shoved diagonally in the corner, and it will still fit entirely inside the strict boundaries of the garage.
The dynamic nature of that analogy perfectly illustrates the concept of bonus tolerance, which is the functional core of the MMC modifier.
It really is.
And it explains one of the most terrifying callouts a young engineer can put on a blueprint: zero positional tolerance at MMC.
Oh man, I've seen machinists completely lose their minds when they see a zero tolerance callout. Because nothing in the physical universe is perfect. The laws of thermodynamics prohibit it.
Oh, they get so angry.
So they look at the print and say, you're demanding infinite precision? This is unmanufacturable.
It causes panic because they're reading it as an absolute zero rather than a conditional zero. The blueprint isn't demanding perfection under all circumstances. It is demanding perfection only when the part is exactly at its maximum material condition.
Ah, okay. Let's apply your garage analogy to a physical flange.
Sure. We have a hole that must be located at a true position so a bolt can pass through it. The blueprint specifies the hole diameter as 10 millimeters, with a tolerance of plus 0.5 millimeters minus 0.
Therefore, the hole can legally range from 10.0 to 10.5 millimeters.
Right. And the MMC of that hole, the worst case scenario with the most metal, is exactly 10.0 millimeters.
So if we apply a feature control frame that calls for a positional tolerance of 0 at MMC, we are stating a conditional rule.
We are saying if and only if the machinist drills that hole at exactly 10,000 millimeters, its center must be located with absolute perfect zero deviation precision from the true position.
Which is Physically impossible.
It is entirely impossible. But here is the brilliant functional trick of the standard. Machinists know they can't hit perfect position, and they know they can't hit exactly 10,000 millimeters.
They don't aim for the absolute edge of a tolerance band. They aim for the middle.
So the machinist uses a slightly larger drill bit and creates a hole that is, say, 10.25 millimeters in diameter.
And because that hole is now 0.25 millimeters larger than the MMC limit, it has departed from maximum material condition.
Exactly. And the standard dictates that whatever amount you depart from MMC, you get to add that exact amount to your positional tolerance as a bonus.
Oh, wow. So the extra clearance created by the larger hole is transferred directly to the location tolerance.
Yes. Suddenly, that terrifying zero positional tolerance has dynamically grown into a 0.25 millimeter tolerance zone.
So if the machinist drills the hole all the way up to its maximum allowable size of 10.5 millimeters, the least material condition, they generate a massive 0.5 millimeter bonus tolerance.
Right. They can drill the hole significantly off-center, and the part is still legally compliant and perfectly functional.
Because a larger, slightly misaligned hole will still allow the mating bolt to slide through just as well as a perfectly positioned small hole.
The MMC modifier is basically a reward system for the manufacturer. It prevents an inspector from rigidly measuring a slightly off-center hole and scrapping a $50,000 titanium component, when in reality the hole was drilled large enough that the mating part would have fit perfectly anyway.
It acknowledges reality over theoretical rigidity. But to communicate all of this without ambiguity, you have to use the right language.
You really do.
This is where we run into the alphabet soup of engineering drawings, which is heavily governed by the ASME Y14.38 standard.
The Dictionary of Drawing Abbreviations.
Exactly. This standard is the legal dictionary. If you aren't meticulous, casually dropping acronyms onto a drawing can cause absolute nightmares.
ASME Y14.38 exists because an ambiguous contract is a failed contract, and the blueprint is the ultimate manufacturing contract. Misinterpreting a standard abbreviation can completely alter the manufacturing process.
Can you give an example?
Sure. For example, in marine engineering, FBT stands for forward ballast tank. In a different context, it might mean something completely different. Or OOR, which is universally out of roundness in pressure vessel mechanics.
I've actually seen a case where someone misinterpreted LMC. We just spent 10 minutes talking about least material condition.
Oh no, what did they think it meant?
I saw an assembly procedure where a junior tech thought LMC meant lower minimum clearance.
You're kidding.
Nope. They fundamentally flipped the math on a critical shaft-to-bearing fit, assuming they needed less space instead of calculating for the least amount of metal. It ruined the entire subassembly.
That is a brutal lesson.
Misunderstanding a single symbol in a feature control frame, or mixing up an acronym from Y14.38, isn't just a typo. It is the literal difference between a complex mechanism sliding beautifully together and creating a very expensive, very heavy paperweight.
The difference between engineering and guessing is precision in communication.
So, assuming your blueprint communication is perfect, your GD&T is airtight, your datums are physical and accessible, we have to take a step back and ask a more fundamental question. Who wrote the physical rules that dictate the thicknesses and materials on that blueprint in the first place?
Right, because you didn't just guess that the wall needed to be 15 millimeters thick.
You certainly shouldn't. Once you know how to dimension the part, you must ensure the part possesses the structural integrity to survive its operating parameters without catastrophic failure or fatigue.
This moves us out of drafting and into the labyrinth of international design codes. For heavy mechanical equipment, specifically pressure equipment, the two global heavyweights are ASME Section 8 and the European Pressure Equipment Directive, commonly known as the PED.
And here's a huge misconception that I see constantly debated on engineering forums. People have this inherent belief that math is an absolute universal truth, right?
They do. They assume physics is physics everywhere.
Right. So if you have a steel cylinder and you put 1,000 psi of pressure inside it, all engineering codes around the world should yield the exact same answer for how thick that steel needs to be to not explode. But they don't. The answers vary wildly.
They absolutely do, and it is often a very bitter pill for engineers transitioning between international markets to swallow. An engineer might run a calculation using a harmonized European standard under the PED and find that a vessel wall needs to be 12 millimeters thick.
Okay, 12 millimeters.
Then they submit that design to a client in North America who runs it through ASME Section 8, Division 1, and the code kicks it back, mandating a 15 millimeter wall for the exact same operating pressure, temperature, and fluid.
So the immediate reaction is, well, one of these codes is wrong. One is unsafe, or the other is massively over-engineered.
Neither is inherently wrong, and both are statistically safe. What you are witnessing is a difference in the underlying philosophical and legal assumptions baked into the mechanics. The standards take totally different approaches to material variance, testing, and inherent factors of safety.
Let's look at the history of those safety factors, because it explains so much. ASME was born out of the horrific boiler explosions of the late 19th and early 20th centuries.
Steamboats and factories just blowing up constantly.
Yeah. Because metallurgy was so inconsistent back then, ASME adopted a heavily conservative approach. For a long time, the design margin on the ultimate tensile strength of the material was 4.0. You had to design the vessel to be 4 times stronger than theoretically necessary to account for invisible flaws in the steel.
Exactly. Over time, as steelmaking improved, ASME reduced that margin to 3.5 in Division 1, and even lower in Division 2 if you utilize design by analysis.
But European codes are different.
Very different. Developing under a different industrial framework, European codes have historically relied far more heavily on advanced, exhaustive material testing up front at the steel mill.
Ah, so they catch the flaws before they build the vessel.
Right. Because they demand tighter controls on the chemical composition and mechanical testing of the steel before it ever leaves the foundry, the PED allows engineers to use a slightly lower factor of safety in their calculations. The result is a mathematically thinner wall, achieving a practically identical level of physical safety.
But regardless of whether you use ASME or the PED, you have to deal with how these codes categorize the enemy of all materials, stress.
Yes, stress categorization is everything.
The days of just running a simple wall thickness equation are over. When you run a modern finite element analysis in FEA, you get a beautiful 3D heat map of your part. But I tell people all the time, you can't just point to a glowing red spot on that screen and declare, the part fails here.
The software is stupid. It just shows you raw numbers.
Exactly. You have to actively categorize that stress based on its physical origin.
If we connect this to the bigger picture, stress categorization is the entire foundation of modern design by analysis. If you don't understand the origin of the force, you cannot predict the failure mechanism. The most critical division in engineering mechanics is distinguishing between primary stress and secondary stress.
Okay, let's break that down.
Primary stress is developed by the imposed loading, which is necessary to satisfy the fundamental laws of equilibrium of external and internal forces and moments.
Let's strip away the textbook definition. You're talking about the raw, undeniable physical forces pushing on the structure.
Exactly.
The most classic example being primary membrane stress. If I have a cylindrical pressure vessel and I fill it with high-pressure gas, that gas is pushing outward equally in all directions, trying to expand the cylinder. The stress is spread evenly across the entire thickness of the steel wall.
It is uniform and pervasive, and here is why primary stress is so lethal. It is not self-limiting.
Explain the physics of that. What do you mean by not self-limiting?
If the internal pressure in that cylinder creates a primary membrane stress that exceeds the yield strength of the steel will cross the elastic limit and begin to stretch plastically.
Right, it permanently deforms.
But the high-pressure gas inside doesn't care that the steel is yielding. The external force remains constant, so the steel stretches. The wall becomes thinner, which means there is less metal to hold the pressure, which causes the stress to increase further.
Wow. So it's a runaway physical feedback loop that results in rapid catastrophic rupture.
It just blows up. The force won't redistribute to a stronger part of the vessel. It just keeps pushing until it pops.
That is terrifying.
Now contrast that terrifying reality with secondary stress. Secondary stress is not caused by an external, relentless load. It is developed by the constraint of adjacent material or by the self-constraint of the structure itself.
So it's fighting itself.
Exactly. It is almost exclusively caused by geometric stiffness mismatches or severe thermal gradients.
A thermal gradient is a great way to visualize this. Imagine you have a really thick, heavy steel pipe in a chemical plant. It's sitting at room temperature. Suddenly, a valve opens, and fluid at 600 degrees Fahrenheit violently rushes through the inside of the pipe.
A massive thermal shock.
Right. The inner millimeter of that steel wall heats up instantly and wants to undergo thermal expansion. It tries to grow. But the outer layers of the pipe wall are still at room temperature. They are cold, rigid, and massive. So the outer wall physically restrains the inner wall from expanding.
Which creates a massive localized compressive thermal stress on the inner wall and a tensile stress on the outer wall. If you ran that in an FEA, the inner wall would be glowing bright red.
So bright red.
The thermal stress might technically exceed the yield point of the material. A junior engineer would look at that and say, the pipe is going to fail. We need to make it thicker.
Which would actually make the thermal gradient worse?
Precisely. Because secondary stress behaves differently. If the thermal stress exceeds the yield point, the inner wall will plastically deform it. It will yield just a tiny microscopic amount. But because the force wasn't caused by relentless gas pressure, but rather by the metal fighting against its own geometry, that tiny bit of yielding actually relieves the thermal mismatch.
Oh, the fight is over.
Yes, the stress self-relieves. Local yielding occurs, the internal structure of the metal shifts slightly, and the massive spike in stress dissipates without the pipe rupturing.
That is wild.
This phenomenon is why the ASME code allows allowable limits for secondary stresses to be much, much higher than primary stresses. The code understands that the material will yield slightly, undergo what we call shakedown, and return to a safe, elastic state.
But, and this is a massive but that destroys pipelines, if that pipe yields back and forth repeatedly, we run into the real-world failure mechanisms.
Yeah.
The valve opens, the pipe heats up and yields in compression. The valve closes, the pipe cools down, and now it yields in tension because it was deformed. Heat up, cool down, expand, contract.
That cycle introduces high-strain, low-cycle fatigue. If you take a metal paperclip and bend it slightly, it holds its shape. But if you bend it back and forth past its yield point repeatedly, the crystalline structure of the metal degrades and it snaps.
That is low cycle fatigue, and secondary stresses are the primary driver of it. You also have to design against plastic instability, which is an incremental collapse or ratcheting over time with each cycle.
And if we are dealing with high temperatures, you can't just worry about cycles. You have to design against creep.
Creep is a terrifying mechanism because it happens while the equipment is just sitting there operating normally.
Creep is the insidious, slow, continuous plastic deformation of a material under a constant stress, specifically at elevated temperatures. Even if your primary membrane stress is perfectly safe, well below the yield point of the steel, if the metal is hot enough, the thermal energy allows the atoms within the crystal lattice to slowly slide past one another. The dislocations within the metal glide and climb.
So the vessel literally swells over time.
Slowly expanding like a balloon over years or decades until the walls thin out so much that it triggers a primary stress rupture. Furthermore, we face stress corrosion cracking, where the combined effects of constant tensile stress and a corrosive chemical environment cause microscopic cracks to rapidly propagate through the grain boundaries of the steel.
To put some hard numbers on how temperature completely rewrites the rules of these codes, let's look at standard flange pressure ratings under ASME B16.5.
Oh, that's a perfect example.
The codes dictate what a standard pipe flange can legally handle based on its material group and pressure class. For example, if you have a Group 1.1 material which covers your standard carbon steels, like SA-105, a Class 150 flange at ambient room temperature is rated to hold roughly 450 psi.
Okay, 450 psi.
If you upgrade to a massive Class 900 flange of the exact same carbon steel, it is rated for 2,225 psi.
And if you go up to the extreme Class 2500, you are looking at managing over 9,000 psi. It's incredible. But the critical lesson is how drastically those legal ratings plummet as the operating temperature increases. That 2,225 psi rating for the Class 900 flange is only legally valid near room temperature. If you run hot oil through that system and heat it up to 600 degrees Fahrenheit, the yield strength of the carbon steel drops. Creep becomes a mathematical factor, and the code aggressively devrates the flange.
The rating drops by hundreds of pounds of pressure just because it got hot. The physics dictate the legality.
But I want to pivot slightly because we keep talking about these stresses happening uniformly. But vessels aren't just straight pipes. The codes make a strict distinction between gross structural discontinuities and local structural discontinuities.
Absolutely do.
Instead of the explain it like I'm five river analogy people always use for stress concentrations, we are really talking about stiffness mismatches here, right? That is exactly the mechanism. A discontinuity is anywhere the geometry of the structure changes, which inherently changes its localized stiffness. Let's look at a gross structural discontinuity. The classic example is the circumferential weld line, where the straight cylindrical shell of a vessel meets the curved hemispherical head.
Under internal pressure, the straight cylinder wants to expand radially outward, proportional to the pressure in its radius. It wants to get fatter.
Right. But the hemispherical head is a completely different geometric shape. Because it's a sphere, it is inherently twice as stiff as a cylinder of the same thickness. It resists expanding outward.
Because they are welded together, they are physically forced to share a boundary. The cylinder tries to expand, the head refuses to expand as much, and they fight each other.
This creates a massive bending moment right at the weld joint. The membrane theory of uniform stress completely breaks down here, and bending theory takes over. This is a gross discontinuity because it affects a large portion of the structure. The entire circumference of the vessel is experiencing this bending moment. It fundamentally alters the overall stress pattern.
So then what constitutes a local structural discontinuity?
A local discontinuity affects a relatively small volume of material and does not drastically change the overall global structural behavior of the vessel. Imagine a small 2-inch instrumentation nozzle penetrating the side of a massive 10-foot diameter tank.
The general cylindrical shell doesn't even know that small hole is there, does it? The overall expansion of the tank is unaffected.
Exactly. But right at the microscopic edge of that drilled hole, the stress flow is completely disrupted. The stress lines have to detour around the hole, bunching up at the edges.
Right at the edge of the hole, the stress might peak to 3 times the normal primary membrane stress of the surrounding shell.
Understanding the mathematical difference between gross and local discontinuities dictates whether you are designing against a global catastrophic collapse of the vessel or just localized fatigue cracking at a nozzle corner.
The transition from the mathematics of the code to the physical reality of the steel brings us to the shop floor reality check. You applied ASME Section 8. You've categorized your primary and secondary stresses. You've mapped your discontinuities. The design is mathematically bulletproof on your computer.
But now it hits the fabrication shop.
And as we established earlier, university taught you that materials are perfectly uniform, isotropic, and well-behaved. The shop floor will quickly teach you that thousands of tons of steel will warp, bend, and aggressively fight back.
The transition from paper to steel is rarely graceful. We primarily see 2 manufacturing methods for heavy pressure equipment fabrication and forging. Forging or extrusion is where seamless pipework is literally pulled or pressed out of a solid billet of red-hot steel. It is structurally superior because there are no longitudinal weld seams.
But forging is severely limited by size. You cannot forge a distillation column that is 20 feet in diameter and 100 feet tall.
No machine on Earth is big enough for that.
To build anything massive, you must rely on fabrication. You have to take flat steel plates, push them through massive hydraulic rollers to bend them into cylinders, and weld the seams shut. And this is the biggest pain point in the industry, dealing with plate thickness during the rolling process.
Plate rolling is an art form masquerading as industrial manufacturing. The specific thickness of the plate dictates the exact nightmare the fabricator will face. Let's look at the extremes. If you are dealing with thin plate, say, a massive diameter vessel, but the pressure is low, so the wall is only 8 millimeters thick,
Your primary enemy is a total lack of rigidity.
heat distortion will ruin you. When you bring the 2 edges of that rolled cylinder together and strike a welding arc to close the seam, you are pumping an immense amount of localized heat into the steel. The molten weld pool expands rapidly, pushing the parent metal away.
But as the weld cools, it shrinks with incredible force.
Because the 8 millimeter plate lacks the physical mass and structural rigidity to resist those thermal contraction forces, the entire cylinder will warp. It will suck inward at the weld seam, creating a localized flat spot or a sharp peak along the joint.
So the immediate engineering thought is, thin plate is floppy and warps under welding heat. Let's just specify thick plate. Let's build it out of 30 millimeter thick steel.
But thick plate introduces the exact opposite metallurgical problem. A 30 millimeter thick steel plate is incredibly stiff. When you force it into the pinch rollers and apply hundreds of tons of hydraulic pressure to curve it, you are forcing the outer fibers of the steel to yield in tension, while the inner fibers yield in compression.
And the steel hates that.
It fights back constantly. When the curved plate finally emerges from the rollers and the hydraulic pressure is released, it experiences springback. A massive amount of elastic energy is stored in the core of the plate that didn't yield perfectly, causing the curve to uncurl slightly.
Anticipating the exact mathematical amount of springback to hit a precise 10-foot diameter is notoriously difficult.
Furthermore, heavily working thick plates cold causes work hardening, which makes it even stiffer. Often, rolling thick plates requires the material to be heated red hot to drop its yield strength, which introduces complex metallurgical phase changes and dimensional scaling that totally ruin your tolerances.
So the metal comes out of the rollers. It's never perfectly round. They tack weld it up, make the final longitudinal weld, and then the mandatory visual and dimensional examinations happen. The third-party inspectors walk out onto the shop floor with their clipboards and flashlights. What are they actively hunting for?
They're hunting for the physical evidence of the fabricator's struggle. They look for arc strikes outside the weld zone, which create localized brittle spots. They look for embedded mill scale that wasn't shot blasted off, which will contaminate the weld chemistry. But most critically, they are looking for bulging and peaking.
Explain bulging. Because I've seen vessels that look like the steel is literally pregnant.
That is the perfect visual. Remember the gross structural discontinuity we just analyzed, the head-to-shell junction. Think about the physical reality of assembling that. The fabricator rolled a massive cylinder, and despite their best efforts, it's slightly oval. It is not perfectly round. And the dished head was pressed in a massive die, and it's not perfectly round either.
So when the crane lowers the head onto the shell, they don't slide together perfectly. There are massive gaps, a severe mismatch.
To close those gaps and get the metal edges touching so they can be welded, fabricators will weld heavy steel brackets called dogs to the shell and the head. They then use massive hydraulic jacks, steel wedges, and turnbuckles to physically force, twist, and crush the shell until it aligns with the head.
Wow.
They force it into submission and heavily tack weld it while it is under immense screaming mechanical stress.
They are essentially locking in thousands of pounds of residual stress before they even strike the arc for the final structural weld.
Exactly. And when they finally perform that heavy multi-pass weld, the localized area where they force the metal together will buckle. It will bulge outward or suck violently inward, leaving a highly visible, permanent distortion. A bulge is not just a cosmetic flaw. It is the physical manifestation of severe, locked-in residual stress that will aggressively lower the fatigue life of the vessel.
And what happens when the fabricator knows the inspector is coming to look for that mismatch? If the weld seam looks ugly and bumpy, the fabricator's primal instinct is to grab an angle grinder and make it look perfectly smooth, right?
That is one of the most insidious dangers in pressure vessel manufacturing. Fabricators will sometimes heavily grind a poorly aligned, bumpy, or peaked seam. They blend it out over several inches so it looks completely smooth and flush to the naked eye. The visual inspector might walk by, shine a flashlight on it, and say, "That is a beautiful, seamless transition."
But the grinder didn't add metal to fix the low spots. It removed base metal from the high spots.
Precisely. By aggressively grinding the parent metal to hide the mismatch, they have actively reduced the effective wall thickness of the vessel below the legal code allowances we just spent hours calculating in the engineering office. They've traded a visible geometric flaw for a hidden, catastrophic lack of structural material. This is why a simple visual check is never enough.
The ASME code mandates rigorous dimensional checks on 5 specific tolerance features of a constructed vessel. Surface alignment to ensure the plates meet flush without excessive offset, straightness of the overall shell, circumference to ensure the volume is correct, the general geometric profile, and critically, circularity, which the industry heavily refers to as out of roundness or OOR.
Out of roundness is a critical mathematical parameter. If a cylinder is perfectly mathematically round, internal pressure creates pure uniform membrane stress in the wall. But if the cylinder is slightly oval-shaped, meaning it is out of round, the physics change. When you pressurize an oval, the internal force actively tries to push it back into a perfect circle.
Because a circle is the most volume-efficient shape for a given perimeter.
Yes. But as the internal pressure pushes the oval walls outward to make them circular, that physical pushing creates severe bending moments within the wall of the vessel. It acts like a beam bending rather than a balloon stretching. And as we discussed with secondary stresses, bending stresses are highly localized and much more damaging. If the vessel is heavily out of round and the pressure cycles up and down, those bending walls will rapidly succumb to fatigue failure. The code strictly limits OOR to typically 1% of the nominal diameter to prevent this.
So here's a practical reality check. If I have a giant distillation column sitting horizontally on roller beds on the shop floor, 50 feet long and 12 feet in diameter, how do I actually measure its straightness or its datums? I can't just hook a flimsy tape measure to the jagged edge of a 50-foot pipe.
You absolutely cannot. The physical edges are often beveled at complex angles for future field welding, or they were just rough cut and irregular. Furthermore, you can never use the longitudinal or circumferential weld seams as your measurement datums. Welds are inherently lumpy, distorted by heat, and inconsistent.
So how do you establish a coordinate system on a giant, featureless steel tube?
To establish a true transverse datum plane, the inspectors use deep center punch marks located 50 to 100 millimeters inward from the final weld seam, directly on the smooth, unaffected parent metal. They straight a precise, perfectly circumferential line all the way around the vessel using a laser level or a wraparound band. That punch line becomes the rigid physical coordinate system. Every subsequent measurement, nozzle elevations, support saddle locations, overall straightness is pulled strictly from those punch marks, completely ignoring the irregularly physical ends of the cylinder.
So let's assume the fabricator did a stellar job. They controlled the heat, they didn't overgrind, the vessel's perfectly round, and the visual inspector signs off on the dimensions. The welder swears on his life that the weld is a perfect full penetration joint, but we still don't truly know what is happening inside the microscopic atomic structure of that steel. The welder says it's perfect. The grinder made it shiny. How do we actually know it won't unzip and explode when we fill it with 2,000 psi of lethal gas? We have to trust, but verify.
Which brings us to the most complex, legally fraught, and heavily debated aspect of pressure equipment construction non-destructive examination, or NDE.
Governed almost entirely by ASME Section V. This is the rule book for how we look inside solid steel without breaking it open. Radiography, which is X-rays, ultrasonic testing, magnetic particle, liquid penetrant. But the actual physics of these tests are only half the story. The history and the philosophy of how we apply them is fascinating. I was reading through the historical transcripts of the ASME Subcommittee V50th Anniversary panel discussion. Hearing guys like E.C. Miller and Dr. Gerald Tenney, the pioneers of industrial radiography, argue back in 1970 give you such an immense appreciation for how hard-fought these regulations were.
The 1970 panel is required reading for anyone in quality control. The core philosophy they fought to establish, and which still dictates global NDE today, is a strict separation of powers. ASME Section V provides the fundamental methods, but the manufacturer must develop the specific written procedures. Section V acts like a physics textbook. It tells you how gamma radiation attenuates as it passes through carbon steel in a broad, generic sense.
It gives you the theory.
Exactly. But theory doesn't inspect welds. The manufacturer's engineering team must write a rigid procedure that says, for this specific 15-millimeter thick SA516 grade 70 carbon steel weld, using this specific iridium-192 isotope at a source-to-film distance of exactly 24 inches exposed for precisely 4.5 minutes, here are the exact steps our technician will follow to prove the weld is sound.
Improving the film is sound brings up the biggest technical debate in the history of radiography. The hole size versus plaque thickness debate regarding radiographic sensitivity. Okay, I need to break down the physical mechanics of this for everyone so they understand why this is such a massive industry pain point. When a technician takes an X-ray of a weld, they don't just shoot the weld blindly. They place a tiny precision-machined piece of metal right next to the weld on the surface of the steel. This is called a penetrometer, or an image quality indicator, an IQI.
The IQI is the absolute foundation of radiographic trust.
This little metal plaque has tiny microscopic holes drilled completely through it. When you develop the X-ray film, that film must clearly show the image of those tiny holes. The logic is simple. If the X-ray technique wasn't sharp enough or sensitive enough to see the artificial, perfectly drilled hole in the penetrometer, then it definitely lacks the resolution to see a jagged, microscopic, real-world crack hidden deep inside the weld. The penetrometer proves the baseline quality of the radiograph.
Correct. If the inspector cannot clearly see the required hole on the film, the entire radiograph is legally void. It must be shot again.
So here is where the misconception occurs, and it causes massive fights between clients and fabricators. A client looks at a specification and says, we want to ensure absolute safety. We want a tighter spec. Let's demand the fabricator use a penetrometer with a much smaller hole. So instead of the standard 0.062-inch diameter hole, the client demands that the technician must prove they can see a tiny 0.040-inch hole.
And the client smugly believes they have just doubled the rigor of the inspection.
But from a purely logical optical standpoint, if I force the NDE technician to find a 0.040-inch hole instead of a 0.062-inch hole, I am proving the film is sharper, right? I am demanding higher resolution of a smaller detail.
You are demanding higher resolution of a two-dimensional plane. But radiography is not a photograph. It is a volumetric density measurement. Shrinking the diameter of the penetrometer hole does not automatically mean the specification is tighter if you allow the thickness of the penetrometer plaque to change. And this is exactly the mathematical trap E.C. Miller was aggressively warning about in 1970.
Explain the trap. Why does the thickness of the little metal plaque matter if I'm just looking at the hole diameter?
Because X-rays don't see holes. They see a difference in the density of mass. When radiation passes through solid steel, a certain amount is absorbed. When it passes through the air gap of the drilled hole, less is absorbed, so that spot on the film becomes darker. It creates radiographic contrast. The contrast is entirely dictated by the volume of the missing metal.
The volume of the cylinder of air created by the hole.
Precisely. If a client demands a smaller 0.040-inch hole, but allows the technician to use a penetrometer plaque that is twice as thick, say, jumping from 0.0075 inches thick to 0.010 inches thick, the physical volume of missing metal might actually be greater than the original wider hole in the thin plaque. A deep, narrow hole in the thick piece of metal creates a much darker, much more obvious shadow on the X-ray film than a wide, shallow hole in a paper-thin piece of metal.
So by demanding a smaller hole diameter, but ignoring the plaque thickness, the client might actually be making the test easier to pass. The deep hole shows up bright as day on the film, the technician passes the test easily, and the client feels falsely secure, claiming they tightened the spec.
Yeah.
It is a fundamental misunderstanding of physics that catches novice quality managers all the time.
Which is why you must understand the geometry of the penetrometer as a whole, three-dimensional system. And this leads directly into the broader engineering approach to NDE, which was another massive topic in that 1970 panel, heavily championed by Mr. Jackson.
The engineering approach is basically the antidote to overspecifying. Jackson's argument was that we don't build every single pressure vessel out of exotic aerospace-grade Incarinal. If a vessel is just holding compressed air for shop tools, we build it out of standard carbon steel because carbon steel is perfectly adequate for that service.
And Jackson argued that the exact same logic must apply to inspection. We should not mandate the absolute highest, most brutally expensive level of 100% volumetric radiography for every single weld we make. It is not economically viable, and it is not structurally necessary.
The level of NDE must match the severity of the design service. If you are designing a vessel that holds highly pressurized lethal hydrogen sulfide gas in the middle of a populated city center, yes, that vessel gets 100% radiography, 100% ultrasonic testing, and magnetic particle on every single nozzle. You spare no expense.
But if you are building a simple, low-pressure water storage tank sitting in the middle of an empty field, mandating 100% radiography is a profound waste of resources. A visual exam, a hydrostatic pressure test, and perhaps some localized dye penetrant are more than sufficient to guarantee safety. NDE must be a calculated engineering decision based on risk, not just a blind blanket adherence to the tightest possible specification to satisfy a lawyer.
But relying on human beings to make those calculated decisions raises an incredibly spicy question, a fundamental tension in the industry that exists today just as much as it did 50 years ago. It's the inherent conflict between the inspector and the examiner, the men and women sitting in a dark room staring at an X-ray film on a light box, deciding if a faint gray squiggle is an acceptable scratch on the film, or a crack that requires them to scrap a $1 million vessel. We have to talk about the massive debate regarding Level 3 personnel qualifications.
This is the ethical minefield of non-destructive testing. To understand the tension, you have to understand the hierarchy. In the NDE world, a Level 3 examiner is the absolute top of the food chain. They are the masters of the physics. They write the complex testing procedures, they train and certify the Level 2 technicians who shoot the film, and crucially, they make the final binding call on highly complex flaw interpretations.
But here's the rub. Outside of very specific, tightly controlled military nuclear programs or certain aerospace sectors, Level 3 examiners are not independent government agents. They are certified and employed by the manufacturer.
The very company that built the vessel.
The company that stands to lose millions of dollars, face massive schedule delays, and potentially incur liquidated damages if the Level 3 examiner looks at an X-ray and says, this massive 5-inch thick weld is cracked. You have to spend the next 2 weeks gouging it out and welding it again.
You immediately see the inherent tension in the quality control system. You have the authorized inspector, or AI. The AI is the independent third-party representative usually employed by an insurance agency or a government jurisdiction. The AI is there to verify that the ASME code was strictly followed. But the code itself often dictates that the acceptability of an imperfection is the sole decision of the examiner.
And the examiner draws their paycheck, their bonuses, and their career advancement from the company that desperately needs that vessel to ship by Friday. It is the literal definition of the fox guarding the henhouse.
Mr. Snyder, one of the ASME panelists, explicitly brought this up in 1970. He noted the difficulty of retaining objectivity when the code delegates the final call of acceptable flaws to the manufacturer's payroll. Who holds the ultimate moral and legal responsibility when an examiner passes a borderline flaw that later propagates into a catastrophic failure? It is a system that relies perilously heavily on the ethics and unwavering professionalism of the NDE community. And to their immense credit, historically, that community is incredibly strong and resistant to pressure. But the systemic structural tension is undeniably real. A production manager screaming at a level 3 to pass a weld so they can hit a quarterly quota happens. The authorized inspector can review the radiographs, and if they spot something egregiously obvious, they can challenge the level 3. But AIs are generalists. They are relying on the manufacturer's specialized level 3 to interpret the murky, subjective gray areas of the film.
It is an entire global safety system built on assumed trust, verified by audit trails, but fundamentally reliant on the unshakable integrity of a single individual looking at a film in a dark trailer at 2 a.m.
Which is why the engineering blueprint and the design code must be conservative enough to survive the occasional human error on the shop floor.
Okay, so let's assume the system works perfectly. The vessel is designed mathematically flawlessly. It is fabricated without distortion. The NDE Level 3 gave the welds a completely clean, ethical bill of health. You are popping the champagne in the engineering office. The project is a success.
But it isn't. Not yet.
No, because now you are at Section 5. Getting it there. The brutal, unforgiving physics of transportation and erection. You have a 500-ton piece of solid steel sitting horizontally in a shop in Ohio, and it needs to be installed vertically on a concrete foundation at a refinery in Saudi Arabia. This is the great blind spot of mechanical engineering. This is where so many flawless designs meet their absolute violent doom.
It is staggering how often transportation is treated as an afterthought. We spend thousands of computer hours analyzing the operational stresses of hot fluid flowing through the vessel. And we entirely forget that putting a massive, rigid steel tower on a flat-bottomed barge and sending it across the open ocean subjects it to dynamic, chaotic forces it will never see in normal operation.
Let's break down the sheer brutality of barge shipping forces. When that vessel is strapped horizontally to the steel deck of a barge, gravity is pulling it straight down at 1.0 WW, being the total shipping weight of the vessel. If the ocean was a perfectly flat stationary table, that would be the end of the calculation.
But the ocean is a dynamic fluid medium. We must design for the marine forces of heave, pitch, roll, and collision. Let's start with heave, which is the vertical rising and falling of the entire ship as it rides over ocean swells.
No, wait, why is heave so destructive? If the boat goes up and down, the vessel just goes up and down with it.
It is about acceleration and apparent gravity. When the barge rides up to the crest of a massive wave and then drops into the deep trough, it is accelerating downward. But when it hits the bottom of the trough, it suddenly decelerates as the buoyancy of the hull fights against the water. This massive deceleration causes the apparent gravity acting on the cargo to spike violently. Furthermore, you have the hydrodynamic added mass effect. The barge has to push thousands of tons of water out of its way to move.
So the vessel suddenly feels much heavier.
Vastly heavier. The classic marine design codes require you to calculate the base tie-downs for a heave force of 1.2 times the total weight of the vessel. For a brief moment in that wave trough, your 500-ton vessel effectively weighs 600 tons, attempting to crush the steel saddles it rests on.
And then you have roll. The boat tipping side to side as waves hit it broadside. The standard lateral force calculation for roll is plus or minus 0.45 W.
Think about the magnitude of that number. Nearly half the entire dead weight of the vessel, 225 tons of force, is actively trying to shear the tie-down bolt sideways and slide the vessel straight off the deck into the ocean.
And if it doesn't slide off, you have to worry about collisions or hard dockings. When the barge hits the pier or tugboats shunted aggressively, the longitudinal force during a collision scenario is calculated at plus or minus 1.5 W.
A force equal to 1.5 times the vessel's weight, 750 tons of kinetic energy, is trying to launch the vessel forward like a massive steel missile. If the transport saddles and the base plates welded to the vessel aren't specifically designed to absorb a 750-ton horizontal shear load, the tie-downs will shear, the vessel will rip its own base plates off, destroy the deck, and sink the barge. The vessel must be designed as a structural chassis first and a pressure container second.
Here's where it gets really interesting. Assuming the tie-downs hold, it survives the violent boat ride. It arrives at the site in Saudi Arabia. Now you have to pick it up. You have to take this 500-ton cylinder from a horizontal resting position to a perfectly vertical standing position. This requires massive cranes, and more importantly, it requires lifting lugs.
A top flange lifting lug is essentially a massive steel ear welded to the very top edge of the vessel. The crane drops its massive hook and cables down, pins into this lug, and begins to hoist.
I was looking at the math for designing these lugs, and the force vectors are incredibly complex because as the crane pulls up, the vessel starts to tilt. The angle of the lifting cable is constantly changing relative to the lug as the vessel rotates from 0 degrees horizontal to 90 degrees vertical.
It is a dynamic stress analysis. You must calculate transverse shear, the lateral force, from the angled cables actively trying to slice the lug off sideways. You must calculate longitudinal shear, the raw vertical force trying to rip the lug straight up out of the weld. And most critically, you must calculate the massive bending stress. As the crane pulls at a severe angle, the cable acts like a giant mechanical lever, applying a bending moment that tries to snap the lug off the flange like a brittle twig.
And there is a massive real-world trap here that literally kills riggers. It has nothing to do with the thickness of the lug. It is entirely to do with the empty space inside it, the pin diameter sizing. You have a massive hole drilled through the lifting lug. The crane drops a heavy steel pin through that hole, connects the shackles, and lifts. What is the fundamental, non-negotiable rule regarding that pin?
The rule dictates that the outer diameter of the lifting pin can be no less than 116 of an inch smaller than the inner diameter of the hole.
So if the hole in the lug is exactly 4 inches in diameter, the steel pin sliding through it must be at least 3 and 16 inches in diameter? A near perfect fit. Why is the tolerance so absurdly tight? What if the rigger is out in the desert, he looks in the rigging box, and he only has a 2-inch pin handy? A solid 2-inch pin made of forged high-strength alloy steel can easily hold 500 tons without shearing in half. Why can't he just drop a perfectly strong but smaller pin into the big 4-inch hole?
Because of Hertzian contact stress, more commonly known in this application as bearing stress, if you put a 2-inch pin inside a 4-inch hole, the radius of the pin does not match the radius of the hole. Therefore, the pin does not sit flush against the curve of the metal. It is resting on a tiny, microscopic sliver of an arc at the very top dead center of the hole.
The contact area between the pin and the lug isn't a broad curve. It is virtually a single, infinitely thin geometric line.
Exactly. And let's look at the basic physics equation for stress. Stress equals force divided by area. We have a massive force, 500 tons of lifting weight. But because the pin doesn't fit, the area of contact is approaching 0.
And as the denominator in that equation shrinks toward 0, the resulting stress skyrockets toward infinity.
Because the contact area is so incredibly small, when you apply 500 tons of lifting force to that single mathematical line of contact, the bearing stress concentration becomes astronomical. It massively, instantly exceeds the ultimate tensile strength of the lug material.
Even if the 2-inch pin itself is strong enough not to break, it destroys the vessel.
The small pin will literally act like a hot wire through butter. It will yield the steel, slice straight up through the heavy steel lug, rip it wide open, drop the 500-ton vessel to the concrete, and kill anyone standing underneath it.
That is horrifying.
By mathematically mandating that the pin must be within 116 of an inch of the hole diameter, you ensure that the curvature of the pin almost perfectly matches the curvature of the hole. This ensures the pin sits completely flush, spreading that 500 tons of force over a massive surface area of steel, driving the denominator up and keeping the localized bearing stress at a safe, elastic level.
That blows my mind. Not because the math is hard, but because of the vulnerability it exposes. Think about the entire journey we just took. This vessel was engineered using advanced finite element analysis to hold thousands of pounds of explosive high-temperature pressure. Its walls are inches thick, forged from certified alloys. The welds were debated by level 3 experts and x-rayed to atomic perfection. The GD&T was perfect, and yet it could be utterly destroyed, bankrupt the company, and take human lives just because a boat swayed aggressively in a wave trough, or because a tired rigger on a Tuesday morning decided to use a lifting pin that was an inch too small. It highlights exactly why mechanical engineering requires holistic, cradle-to-grave thinking. You aren't just designing a static pressure container in a vacuum. You are designing an object that must survive the human, physical, and environmental chaos of the real world.
Which is why we also have to obsess over the trunnions. Trunnions are the massive, heavy-walled pipes welded to the side of the vessel, lower down near the center of gravity. We use them as tailing devices during the lift. When the main crane lifts the top flange, a secondary tailing crane holds the trunnions to keep the bottom of the vessel from dragging on the ground as it swings.
And the forces there are just as complex as the top lug.
Even more so. When the vessel is horizontal, The tailing crane lifting on those side trunnions creates a massive torsional moment, a twisting force that tries to wring the cylindrical shell like a wet towel. As the vessel rotates and becomes vertical, the force vector shifts. It creates a severe longitudinal bending moment, acting like a lever trying to rip a gaping hole in the side of the vessel wall.
Which means the thin shell of the vessel can't handle it alone.
Rarely.
Mm.
Accommodating those temporary lifting loads requires the engineering team to design massive external reinforcing pads welded around the trunnions, and often massive internal structural steel rings inside the vessel just to prevent the shell from buckling. We undergo meticulous weld analysis, fatigue calculations, and hundreds of thousands of dollars in added material and fabrication time.
All for a temporary lifting operation that lasts, what, 20 minutes?
Usually less.
Yeah.
20 minutes of lifting literally dictates the structural architecture of the entire internal vessel.
Which leaves us with a fascinating paradigm shift, a final, provocative thought to mull over as we wrap up this masterclass.
Yeah.
What if the entire industry has this backward? What if we stop thinking of shipping barge dynamics and crane erection as secondary transportation problems that we just tack on to the end of the design process?
It is a vital question. What if, from the very first day of drawing the CAD model, we treated the violent boat ride and the 500-ton crane lift as the vessel's primary, most volatile operating environment? How would that paradigm shift fundamentally change the way we design our base plates, our internal skirts, and our transport saddles from day one? If we prioritize engineering for the brutal journey first, does the static destination simply take care of itself?
School taught you engineering. The shop floor will teach you wisdom. Don't forget, follow any ad. If this helped you even a little, please tell us. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching and teaching. If you're on a journey trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing. Also, don't forget to check out our YouTube.